apresentação. Bom dia. Em nome do Reitor da Universidade do Minho, declaro aberta a cerimónia de atribuição do Doutoramento Honoris Causa ao professor Duncan Haldane. Iniciamos esta sessão ouvindo, em pé, o hino da Universidade do Minho. Tomará agora a palavra o Presidente da Escola de Ciências da Universidade do Minho, professor José Manuel Meijome.
Good morning. With permission of the Rector Magnificus of the University of Minho, Professor Pedro Areces, whom I commend, and in your person I greet all academic, civil, ecclesiastical authorities, fellow professors and researchers, technical staff, students, partners, dear guests, ladies and gentlemen. On behalf of the School of Science, whose Scientific Council unanimously supported the awarding of this honoris causa doctorate, I want to address you a warm and brief message. Today, we have the great privilege of welcoming Professor Duncan Haldane as he joins the College of Doctors of the University of Minho. This is a moment of genuine pride for our university and our distinguished partners at the International Iberian Nanotechnology Laboratory. Professor Haldane, we are deeply honored by your presence within our academic community today. In the scientific world, Professor Haldane is universally recognized as one of the great architects of modern theoretical physics. His groundbreaking contributions to the understanding of quantum matter have reshaped the way we think about the fundamental properties of materials and the behavior of electrons in low-dimensional systems. By revealing the deep and unexpected role of topology in condensed matter physics, his work opened an entirely new avenues of research and technological development that continue to inspire generations of scientists across the world. For the School of Science at the University of Minho, which seeks to cultivate curiosity, rigor, and creativity in the pursuit of knowledge, the opportunity to celebrate a scientist whose ideas transform the entire field is profoundly meaningful. It reminds us that science advances not only through incremental progress, but also through the bold insights in challenge our intuition and redefine the boundaries of our understanding. Today's ceremony carries a significance that extends far beyond this beautiful hall. Among us are students and young researchers who are taking their first steps into the scientific world. The witness, the recognition of a career such as Professor Haldane's one is to be reminded that fundamental science, sometimes abstract, hard to take, often difficult to pursue without immediate application, has the power to deepen our understanding of nature, reshape technology, and transform our world. As a School of Science starting its 6th decade of existence, we are also reflecting on our past and looking into our future, on how we will educate, how we will conduct research, and how we will contribute to the advancement of knowledge. Moments like this remind us that why universities exist, to create environments where curiosity is encouraged, where fundamental questions are pursued with intellectual freedom, and where young minds are inspired by the achievements of those who came before them. One of the enduring lessons of Professor Haldane's works is precisely this, that the most profound discoveries often emerge from the courage to explore ideas that initially seem to be purely theoretical. The conceptual tools that arise from this exploration have the potential to become the foundations of future technological revolutions. Professor Haldane, thank you for the extraordinary clarity and depth with which you have expanded our understanding of the quantum world. Thank you for showing us that creativity and intellectual courage remain at the heart of great science, for your contributions to the humanities' knowledge, and for ensuring that we will have a better future with science. Thank you.
Segue-se a atribuição do título de Doutor Honoris Causa em Física ao professor Duncan Haldane. Peço desculpa o lapso da minha parte. Usará naturalmente agora da palavra, neste caso a madrinha, a professora Clívia Sotomayor Torres.
Good morning. Magnificent Rector, distinguished members of the Senate, ecclesiastical authorities, honored guests, ladies and gentlemen. It is a great honor and privilege to present Professor Frederick Duncan Haldane, one of the most influential theoretical physicists of our time, whose work has profoundly reshaped our understanding of quantum matter. Professor Haldane is internationally recognized for revealing how topology, a branch of mathematics concerned with global geometrical properties, can play a central role in the electronic properties of materials. His discoveries opened entirely new directions in condensed matter physics and laid the conceptual foundations for what is known today as topological phases of matter. Professor Haldane was born in London in 1951, and he was a very curious student and scholar. He went to Christ's College of the University of Cambridge and studied physics, but also had an interest in biology and chemistry. He encountered ideas that would shape his scientific trajectory, attending the lectures of Philip W. Anderson, who was one of the most influential condensed matter physicists of the 20th century, and himself a Nobel laureate in 1977. Inspired by Anderson's deep and conceptual approach to quantum many-body problems, Professor Haldane student Haldane at the time decided to pursue his doctoral research under his supervision. He completed his PhD in Cambridge in 1978 with a thesis entitled An Extension of the Anderson Model as a Model for Mixed Valence Rare Earth Materials. He later on worked at the Institut Laue-Langevin in Grenoble, which is one of Europe's leading centers for research in Newton sciences. And in 1981, he joined the University of Southern California as an assistant professor. After staying in Bell Labs in New Jersey, he joined Princeton University in 1990, where he has remained a central figure in theoretical physics ever since. One of Professor Haldane's earliest and most influential achievements was the formulation of the Luttinger liquid theory. In three-dimensional metals, the behavior of interacting electrons is described by Landau's Fermi liquid theory, where the low-energy excitations resemble weakly interacting quasiparticles, and for decades, this framework dominated the theoretical descriptions of electronic systems. However, when electrons are confined to one dimension, this fails dramatically. In a seminal paper in 1981, Professor Haldane demonstrated that interacting quantum fluids in one dimension form a completely different universality class. Haldane's great insight was to recognize that the strange behavior found in several exactly solvable one-dimensional models was not an accident, but instead a universal interacting quantum fluids in one dimension, which form a new state of matter, and a universal one. Interacting quantum fluids in one dimension then were known as, or were baptized as, Luttinger liquids. The importance of this is that when electrons cease to exist as quasiparticles, they fractionalize into collective excitations of charge and spin. In these systems, the fundamental excitations are not electron-like quasiparticles, but collective modes of charge and spin. A very striking consequence of this theory is that one separates spin and charge. The electron normally is thought to have spin and charge simultaneously. As a single particle, effectively now is fractionalized into independent excitations that propagate with different velocities. So Professor Haldane's insight showed that the behavior found early in exactly solvable Luttinger models is in fact universal, and it governs a broad class of one-dimensional quantum systems. So this work inaugurated an entire new field of research and continues to influence the study of quantum wires, spin chains, and strongly correlated materials. In 1983, I'm going back, Professor Haldane made another breakthrough that transformed our understanding of quantum magnetism. By analyzing the long wavelength fluctuations of quantum spin chains, Professor Haldane showed that the system can be mapped onto a nonlinear sigma model, which is a field theory widely used in particle physics. And that allowed him to predict the antiferromagnetic spin chains behaving fundamentally different depending on whether the spin is integer or half. As it was initially received with disbelief, as it happens in science, by part of a community, it was initially referred as the Haldane conjecture. So, conjecture, integer spin chains possess a finite energy gap between the ground state and the excitations, and the half-integer spin chains do not have a gap. These predictions of a gap reveal something even deeper. With the nonlinear sigma model, the effective theory contains a topological term, meaning that the physics depends not only on the local interactions, but also on the global properties of a quantum field. In this way, topology, concerned with properties that remain unchanged under continuous formation, enters the description of quantum matter and determines whether excitation spectrum is gapped or gapless. This result was confirmed experimentally and by subsequent theoretical and computational work. The microscopic Hamiltonians describing these spin chains look identical, but their energy, the low energy physics, differs quantitatively for integral and half-integer spins. The prediction of a gap in integer spin change was also a striking example of emergence, a new energy scale absent from the individual spins themselves, which arises collectively from the interaction between them. So 81, 83, and in 88, Professor Haldane continued and studied the quantum Hall effect without Landau levels. So his work played a decisive role in the emergence of topological condensed matter physics, having revealed how topology could shape the excitations of quantum spin chains. He went on to show that topology could also govern the behavior of electrons in solids. He introduced a remarkable theoretical model of electrons moving in a honeycomb lattice, a structure very similar to graphene, showing that a material could exhibit quantized Hall conductance even in the absence of an external magnetic field. This model demonstrated that quantum Hall physics can arise purely from the topological properties of electronic band structures. Today, this system is known as a Haldane model, and it represents the first example of what we call a Chern insulator or a quantum anomalous Hall system. The key insight is that the global structure of quantum wave functions can be characterized by an integer topological invariant called the Chern number. When this is non-zero, the system exhibits robust edge currents and quantized Hall conductance that are immune to disordering and imperfections. This conceptual breakthrough provided the foundations for the modern field of topological insulators and topological quantum materials, which has become one of the most vibrant areas of contemporary condensed matter physics. The impact in modern physics has shown that the influence of Professor Haldane's ideas extends far beyond the original systems in which they were formulated. Topological concepts introduced in condensed matter now appear in photonics, in cold atom gases, plasmonics, phononics, and electrical circuits. So what began as a deep theoretical insight into quantum matter has grown into a broad scientific revolution. More recently, Professor Haldane also contributed to a deeper understanding of quantum phases through the concept of entanglement spectrum. By analyzing the spectrum of eigenvalues obtained when a quantum many-body state is partitioned into two subsystems, he showed that patterns of quantum entanglement can reveal the hidden topological structure of a state. This insight established a powerful bridge between condensed matter physics and quantum information science, where entanglement is a central resource and provided a new tool to identify and classify topological phases of matters. To summarize, a striking feature of Professor Haldane's work is that many of his most influential contributions concern one- and two-dimensional quantum system. These reduced dimensions, quantum fluctuations, and topology give rise to an entirely new form of collective behavior that have no counterpart in three-dimensional materials. And today, such low-dimensional systems lie at the very base of nanoscience, where materials are engineered and controlled at the atomic scale, whether in graphene, quantum wires, or atomically precise spin chains. So by revealing how topological principles govern quantum matters, Professor Haldane has transformed theoretical condensed matter physics and opened pathways that continue to shape the frontiers of science. I have to thank my colleague, Joaquin Fernandez-Rosier, who helped me with this Laudatio. Thank you very much.
Seguindo no elogio ao doutorando, ouviremos agora o professor Mikhail Vasilevsky.
Magnificent Rector, dear colleagues and students, honorable guests, ladies and gentlemen, it is a great honor for me to have the opportunity to say a few words about Professor Duncan Haldane, an outstanding theoretical physicist who works in the field of condensed matter. Professor Haldane was among the first to demonstrate that topology can fundamentally determine the behavior of quantum materials, thereby opening an entirely new direction in our understanding of phases of matter. In particular, he predicted that one-dimensional quantum spin chains behave differently depending on whether the spin is integer or half integer, a result now universally known as the Haldane conjecture. He further proposed a theoretical model showing that a material could exhibit the quantum Hall effect without the presence of an external magnetic field. This model, now known as the Haldane model, became foundational for the modern field of topological insulators. In recognition of his discoveries of topological phase transitions and topological phases of matter, Professor Haldane was awarded the Nobel Prize in 2016, together with David Taules and Michael Kosterlitz. As stated in the press release issued by the Swedish Academy of Sciences, Duncan Haldane discovered how topological concepts can be used to understand the properties of chains of small magnets found in some materials. Duncan Haldane was born in England into a family of medical doctors, and from early age he showed a strong interest in mathematics and natural sciences. He entered Christ's College at the University of Cambridge in 1970, where the curriculum required the study of 3 subjects in addition to mathematics. So he chose cell biology alongside physics and chemistry. In his final undergraduate year, he attended an advanced course on the quantum mechanics of solids taught by Professor Philip Anderson, winner of the Nobel Prize in physics in 1977. And that experience proved decisive for the scientific path of Duncan Haldane. He completed his PhD in 1978 under Anderson's supervision. Professor Haldane's scientific contributions are both numerous and profound. most of them have been mentioned by Professor Clivia. I will mention them as well, perhaps with less detail. Between 1980 and 1983, he introduced and developed the concept of the Latinger liquid, demonstrating that interacting systems in one spatial dimension exhibit universal low-energy behavior independent of microscopic details. He showed that fermionic systems can be treated using so-called bosonization, that is, re-expressing fermionic degrees of freedom in terms of collective bosonic modes. And that elementary excitations, usually seen as electron-like quasi-particles, in strongly correlated one-dimensional electronic systems may be described by anionic statistics, which is a generalization of the known Fermi-Dirac and Bose-Einstein statistics. Professor Haldane also introduced the model of topological quantum numbers associated with quasi-particles. In 1983, he formulated the Haldane conjecture concerning antiferromagnetic spin chains. Integer spin chains possess an energy gap between the ground and excited states, while those with half-integer spin do not. This part was explained by Professor Clivia. I just add that this discovery was unexpected for theorists, but it was proved experimentally in the subsequent years. Still in 1983, Professor Haldane published a particularly influential article on the fractional quantum Hall effect, where he proposed that the fractional quantum Hall states form a hierarchy of incompressible quantum fluids built from quasi-particle condensations. The so-called Haldane-Halperin hierarchy became one of the main theoretical frameworks in the context of the fractional quantum Hall effect. This phenomenon, where quasi-particles carry a fractional charge, electric charge, is one of the most surprising in condensed matter physics. In 1988, Professor Haldane introduced what is now known as the Haldane model, a fermionic model in which electrons propagate on a honeycomb lattice, similar to graphene, and can exhibit quantum conductivity analogous to that of the integer quantum Hall effect, yet without a magnetic field and without Landau levels. He introduced a topological characterization of this system through the so-called Chern number, which distinguishes trivial from topological phases. The essential insight is that certain fundamental properties of matter are determined not by local microscopic structure, but rather the topological nature of the system encoded in the Chern number. Its importance was recognized by the Dirac Medal Award in 2012. So please allow me to take some minutes to recall briefly the context of the seminal 1988 paper published by Professor Haldane in the Physical Review Letters, entitled Model for a Quantum Hall Effect Without Landau Levels, Condensed Matter Realization of the Parity Anomaly. To explain the context of this work, for non-specialists, I need to jump back in the history of physics. In 1879, Edwin Hall discovered that when a metal carrying an electric current is placed into a magnetic field, there is a voltage across the conductor, which is transverse to the electric current and perpendicular to the applied magnetic field. The ratio between the Hall voltage and the electric current is called Hall resistance. It is simply proportional to the magnetic field magnitude for conventional conductors and depends on several parameters of the material. The Hall effect became one of the main techniques to characterize conductors. In 1979, Klaus von Klitzing discovered that for a two-dimensional conductor, the Hall resistance assumes discrete values, which only depend on fundamental constants, Planck constant and electric charge of the electron. The quantization is extraordinarily precise and independent of material details. This experimental discovery thrilled theoretical physicists, and in the consequent years, step by step, the integer quantum Hall effect was understood. I will not explain it in detail. The essential things are the following. The strong magnetic field creates discrete quantum states called Landau levels. Only Landau levels pinned to the boundaries of the conductor, called edge states, carry electric current in the transverse direction. Each edge state works as a one-dimensional channel and contributes precisely a quantum of charge squared divided by the Planck constant to the Hall conductivity. Natural disorder present in any real sample due to impurities and defects is essential for the observation of the integer quantum Hall effect. In an ideal structure, the quantized values of the Hall resistance wouldn't be observable. But how can it be that in a real structure with disorder, absolutely unique in details, the number C in the Hall resistance is an exact integer? There is a hint which comes from the mathematical theorem called Gauss-Bonnet theorem, which links the integral of the curvature of a surface to its underlying topology through an integer number called genus. A continuous deformation of a two-dimensional surface does not change its genus. Put simply, a torus always has one hole, even if we deform it but do not tear. Genus 1. While a sphere has no holes, even if we stretch or flatten it a lot, but do not pierce it. Genus 0. It is possible to introduce an analog of genus in mathematical topology for electronic states in condensed matter, which is exactly the Chern number. This integer number distinguishes topologically trivial phases and non-trivial electronic states in condensed matter. In 1988, Professor Haldane posed the bold question whether a non-zero Chern number and quantized Hall conductivity could arise without an external magnetic field. He proposed a tight binding model on the honeycomb lattice that introduces sublattice asymmetry and breaks time reversal symmetry through imaginary hoppings between next to nearest neighbors. He demonstrated that the two bands that arise in this model carry opposite and non-zero Chern numbers, plus minus 1. This model is now recognized as the prototype of the quantum anomalous Hall effect, or Chern insulator. To conclude, Freeman Dyson, a famous physicist and mathematician, said in his lecture delivered in honor of Albert Einstein, "Some scientists are birds, others are frogs. Birds fly high in the air and survey broad vistas of science. They delight in concepts that unify our thinking. Frogs live in the ground below and see only the flowers that grow nearby." Dyson characterized himself as a frog. I think Professor Haldane is a bird. It is difficult to overestimate the impact of Professor Haldane's fundamental contributions. By transforming elegant and exactly solvable models into general principles of nature, he has reshaped our understanding of quantum matter and established a new paradigm in condensed matter physics. It is therefore with the highest respect and admiration that we celebrate and honor him today. Thank you very much.
Agora o momento em que visualizaremos um pequeno vídeo que resume a vida e carreira do professor Duncan Haldane. Duncan Haldane é um físico britânico conhecido pelas suas contribuições fundamentais à física da matéria condensada. Filho de um médico escocês e mãe eslovena, nasceu em Londres em 1951 e possui tripla cidadania, britânica e eslovena, sendo atualmente cidadão com residência permanente em New Jersey, nos Estados Unidos. De resto, é aí que exerce, sendo professor na Universidade de Princeton. O seu interesse pela física na escola, através do fascínio por coleções de cristais e minerais. Nos anos 60, durante a juventude em Londres, interessou-se pela contracultura e pelo rock. Aprecia ouvir música e ler nos tempos livres. Tem um interesse profundo na história da sua família, tendo realizado investigações detalhadas sobre a linhagem dos Haldane. Estudou na Universidade de Cambridge, doutorou-se em 1978 e teve passagens por Grenoble, na França, no Institut Langevin, pela Universidade do Sul da Califórnia e pela Universidade da Califórnia em San Diego, antes de se juntar a Princeton. Haldane é conhecido por utilizar métodos teóricos e matemáticos para prever comportamentos exóticos da matéria em escalas atómicas. A sua obra revolucionou a compreensão de sistemas magnéticos e materiais semicondutores, incluindo a teoria dos líquidos de Luttinger e o efeito Hall quântico fracionário. Em 2016, compartilhou o Nobel com David Fowles e Michael Kosterlitz por descobertas teóricas sobre transições de fase topológicas e fases topológicas da matéria. Além do Nobel, recebeu o prémio Oliver E. Buckley de matéria condensada em 1993 e a medalha Dirac em 2012. Peço agora ao doutorando e aos padrinhos que se dirijam para junto do reitor para a imposição das insígnias doutorais. Professor, please join the rector.
Eu, Pedro Areses, reitor da Universidade do Minho, declaro o professor Duncan Haldane como doutor honoris causa desta universidade na área de conhecimento da física e confio ao Sr. professor Mikhail Vasilevsky a distinção de o distinguir com as insígnias desta universidade, insígnias de doutor desta universidade. Muito obrigado.
Pela grandeza da sua obra, pela importância das suas contribuições, pela sua capacidade de revelar a profundidade da física com modelos analíticos simples, solicito a atribuição do título de doutor honoris causa na área de conhecimento de física ao professor Duncan Haldane.
Vai usar da palavra o novo doutor Duncan Haldane. Professor, please.
Obrigado. It's indeed an honor to receive the Doctor Honoris Causa of the University of Minho, following in the footsteps of my good friend Alan Aspe 2 years ago. These awards are related to what some are calling the second quantum revolution, 100 years after the birth of quantum mechanics. While the laws of quantum mechanics that emerged in the short period 1925 to 32 have not changed since they were discovered, they did not immediately reveal to us all the strange and remarkable phenomena that they allow. Indeed, after 150 years, we are still learning about the unexpected things that the laws of electromagnetism allow, such as photonic crystals. So success in a scientific career is a combination of good luck and preparation. As scientists, we have the driving force of curiosity that can generate luck by taking us on a path that occasionally may lead a few of us close to some remarkable properties of nature that no one, including ourselves, had expected to exist, like a hidden treasure. These discoveries often transform a field of science, showing new ways to think about nature. I think that anyone working in basic science who is able to take the time to explore unexpected things that might show up along their scientific path and has the preparation to recognize them has a tiny but finite chance of making one of these discoveries that impacts their field enough to be recognized with a Nobel Prize. I had the great fortune to be mentored by the brilliant and unorthodox thinker Philip Anderson, who taught me the power of what were sometimes disparaged as simplified toy models, stripped of irrelevant, complicating details, while they retained the underlying physics of a phenomena that we are trying to understand. Around 1980, two apparently unrelated, unexpected examples of what we now call topological states were discovered, topological quantum states were discovered. One experimentally, the two-dimensional integer quantum Hall effect, unexpectedly discovered by Klaus von Klitzing, and the other, my toy model discovery that the quantum ground state of a one-dimensional antiferromagnetic spin chains with integer and half-integer quantization of the spins was very different, depending on whether the spin quantum number was integer or half-integer. Interestingly, the spatial location of these discoveries in neighboring laboratories in Grenoble, France, was also close. Both discoveries were unexpected and accidental. Later, it was realized that both were topological properties that can be classified by integers, unlike conventional properties that are represented by real numbers that one measures. The birth of quantum mechanics came from the realization that properties of individual atoms were discrete, but it had not been understood that macroscopic quantum phases of matter could also be classified by integers. This is the essence of topology, as in the classification of smooth, closed two-dimensional surfaces by the integer number of holes they have, like a donut or a pretzel, or equivalently by the number of handles they have, like a teacup or a loving cup. Topological states are robust. A significant amount of force must be exerted to change the shape of a football into a donut. In the quantum examples, an energy gap must break down to allow the more abstract topology to change between classes labeled by different integers. And the topology is essentially that of quantum entanglement within the materials, where quantum entanglement is the central theme of the so-called second quantum revolution. Some very interesting schemes for using topological states to store and process quantum information in a robust way that protects it and hides it from the local environment, which can degrade it, have been theoretically developed, and Microsoft have been trying to implement them physically. Over the course of my career, I've seen how the way that we think about quantum properties of condensed matter has completely changed as a consequence of these new ideas. And it's been very gratifying to have participated in some of these changes,
and see how my work has been built on by others to reveal more and more exciting developments, such as three-dimensional topological insulators that had remained undiscovered over years of large-scale ab initio computational studies, because no one had expected their existence until the toy models revealed them. Most of these changes have come about through novel insights by individual scientists that artificial intelligence, at least of the type that has emerged in recent years, could not have had. It's an exciting time for young people to be involved in new developments in quantum physics and quantum technologies. While we're still waiting to see how quantum information processing will turn out, there's a new generation of ultra-precise quantum sensor devices which will precede this and change what is possible. We're having an exciting Iberian workshop on quantum topological states here at Braga next week, and I hope to hear about exciting work by many young scientists. Thank you again for the honor you have accorded me here at the University of Minho.
Vai proceder-se agora à entrega da carta doutoral. Professor Duncan, please join the rector again. O novo doutor aproxima-se assim do reitor para receber a carta doutoral. Tomará agora a palavra o reitor da Universidade do Minho, professor Pedro Areces.
Muito bom dia a todos. Caro professor Duncan Haldane, mais novo membro do Colégio de Doutores da Universidade do Minho, Senhor Presidente da Escola de Ciências, caríssimo professor José Manuel Meijom, caros padrinhos, professor Mikhail Vasilevski e professora Clívia Sotomayor Torres, Excelência Reverendíssima Dom José Cordeiro, Arcebispo Primaz de Braga, Senhor Reitor da Universidade Fernando Pessoa, caro professor Eugênio Ferreira, caras e caros colegas da equipa reitoral, senhores membros dos órgãos de governo e de consulta da Universidade do Minho, estimados representantes autárquicos e demais autoridades aqui presentes, caros presidentes e vice-presidentes das unidades orgânicas de ensino e investigação da Universidade do Minho, senhoras e senhores professores e investigadores, com um cumprimento especial para os colegas da Escola de Ciências e do INL, hoje aqui presentes, caras e caros dirigentes e demais trabalhadores técnicos, administrativos e gestão da Universidade do Minho, uma palavra especial para os estudantes que quiseram participar também nesta cerimónia, caras e caros convidados, minhas senhoras e meus senhores. Chegamos ao momento final desta cerimónia, um momento de particular significado, um momento que assinala uma das mais emblemáticas expressões da vida universitária, a atribuição do grau de Doutor Honoris Causa. Este é um instante raro, é um instante impregnado de júbilo, um instante em que a Universidade afirma de forma inequívoca e solene os valores que a define e as referências maiores que decide celebrar e perpetuar. Permitam-me, antes de mais, dirigir uma palavra muito especial ao professor Duncan Haldane. And now a few brief words in English. Professor Haldane, thank you very much for accepting our invitation. Your willingness to join us and your enthusiasm are a true honor to the University of Minho. Quero também agradecer aos padrinhos e ao Presidente da Escola de Ciências e, na vossa pessoa, a todos os membros da Escola e do INL. Agradeço igualmente a todos os presentes, cuja participação confere ainda maior dignidade a esta cerimónia. Minhas senhoras e meus senhores, hoje homenageamos uma figura maior da ciência mundial. O percurso e os contributos do professor Haldane ficaram aqui amplamente explicitados e evocados. Sabemos que estamos perante um percurso excepcional, reconhecido ao mais alto nível, nomeadamente com a atribuição do Prémio Nobel da Física em 2016 e entre muitas outras distinções de reconhecido prestígio que recebeu ao longo da sua notável trajetória. Mais do que repetir estes méritos, importa sublinhar o seu significado. O grau de Doutor Honoris Causa não se limita a distinguir a excelência científica. Consagra, acima de tudo, valores como a liberdade de pensamento, o espírito crítico, a coragem de ultrapassar fronteiras do conhecimento, sempre guiados pelo respeito pela dignidade da pessoa humana. Distingue percursos de vida extraordinários, caminhos marcados pela dedicação pessoal, pelo rigor científico e pela visão inovadora e transformadora. E distingue aqueles cuja contribuição tem impacto decisivo no progresso da sociedade. É justamente esse legado, que é de sabedoria, mas também de inspiração, que hoje nos reúne aqui para celebrar. Ao atribuir este título, a Universidade do Minho presta uma justa homenagem ao contributo notável do professor Duncan Haldane para a ciência e para a comunidade científica internacional. Um contributo de particular relevância numa era de rápido avanço tecnológico, marcado por desenvolvimentos notáveis nos domínios da nanociência e da nanotecnologia. Trata-se, talvez acima de tudo, de um contributo que reafirma o valor da ciência fundamental. A ciência de base que permanece como um dos alicerces fundacionais do progresso e do desenvolvimento das sociedades. Ao celebrarmos aqui o professor Duncan Haldane, não distinguimos apenas o cientista brilhante. Celebramos a essência da universidade, a busca permanente pelo conhecimento, a coragem de desafiar o desconhecido e a nossa profunda convicção de que a ciência é uma luz que ilumina o futuro. Este doutoramento honoris causa relembra-nos que, hoje como sempre, a grandeza da investigação científica não se mede apenas através do conhecimento que construímos até aqui, mas pelo que nos atrevemos a imaginar e a começar a construir. Minhas senhoras e meus senhores, esta decisão deve ser entendida à luz da missão da Universidade do Minho. Criar conhecimento, disseminá-lo e colocá-lo ao serviço da sociedade, promover o pensamento crítico, estimular a inovação e contribuir para um desenvolvimento sustentável e mais justo. Vivemos hoje numa era de extraordinários avanços científicos e tecnológicos, mas vivemos também num tempo em que surgem narrativas que questionam e por vezes até negam esse mesmo avanço e tal conjuntura deve suscitar preocupação. É por isso que o exemplo que hoje celebramos se torna ainda mais relevante, servindo-nos de inspiração, porque reafirma o valor da ciência como pilar do conhecimento e como base do progresso. Estimado professor Duncan Haldane, agradecemos profundamente o exemplo que nos oferece, um exemplo de dedicação à ciência, de rigor intelectual e de compromisso com um mundo melhor. Agradecemos também a sua generosidade para partilhar connosco o seu saber e a sua experiência. É por isso, com imensa honra e alegria, que acolhemos no corpo de doutores da Universidade do Minho o professor Duncan Haldane. Muito obrigado a todos.
De seguida, todos em pé, ouviremos o hino académico Gaudeamus. Em nome do reitor, declaro encerrada esta cerimónia, que terminará com a saída do cortejo académico. Aos restantes convidados, peço que aguardem na sala para a indicação de saída. Seguem-se os cumprimentos ao novo doutor, que decorrerão no hall desta reitoria. A todos, muito obrigado pela vossa presença.